Good afternoon, everyone. The topic for today is diving physiology, and the first part, the first micro lecture here, will have to do with breath hold diving and shallow water blackout. Essentially, if you look at the current records for how long can a human person hold the breath, you see that the results are rather astounding. Basically, what's called static apnea goes down to or just as long as 11 minutes, 35 minutes for a man, Stéphane Mifsud, French, or 9 minutes for women. If you're interested, these records change all the time. Actually, not the men's, this is from 2009, but these records tend to change over time. You just have to go to this website and you'll get the most updated information. There are lots of different categories, and I'm not going to bother to tell you about this, but basically this is static apnea. This is how long can you hold your breath. That's it. Constant weight apneas, this is basically apnea going underwater as deep as you can, and how deep you can reach. Basically, for men, 128 meters, 101 meters. Constant weight apnea. There are other modalities in which you can go even deeper, or some other modalities in which you have no fins or fins, whatever. Just so that you can compare the basic capabilities of what some people, trained people, can do. These records would have been predicted to be impossible by physiologists. So, you know, it's possible to go over what physiologists could predict. Same thing happened, I think I've mentioned this before, that the physiologists predicted that men could not climb Mount Everest without additional oxygen. And that was done. In terms of safety, though, current records are, at best I say, marginally safe. You are pushing it. You are pushing it. And then it's not a surprise that these people that practice apnea, extreme apneas, tend to die more often than the normal population. What are the physiological challenges while breath hold diving? There are quite a few. Depends on exactly what you're doing. But if you are diving into the sea, you have a need to equilibrate pressure across the eardrums involving Valsalva maneuvers during descent, essentially because there is an increase in pressure, and this increase in pressure is affecting your tympanic membranes, and that is felt, a need to compensate. This is one small thing. Cold stress. Water will basically suck as much heat as it can, so cold stress resulting potentially in a hypothermia. Lung compression due to pressure, the pressure at depth, and also the increased pressure of alveolar gases. You can compare this if you dive, or in a dive down to 133 meters of depth, lung volume will be reduced to 1/14 of the original. Why is that? Because at 133 meters, the pressure underwater is 13 atmospheres plus the atmosphere that is at the surface, that's 14 atmospheres. So a reduction of, or the reduction in volume down to 1/14 of the original. So you would go from a typical lung capacity around a bit below 10 liters down to less than 1 liter, which is a volume much lower than the residual volume. You could say, well, how does that not injure the chest? Well, the chest is not injured because there is a general compression of the rib cage, elevation of the diaphragm, and blood being redistributed to the heart and vascular bed in the chest. So basically, there is a distribution of blood, there is a redistribution of spaces, there's no crushing by the pressure. It's been calculated, it's been measured in humans diving to 40-50 meters that about 1 to 1.5 milliliters of blood are actually relocated during this diving. How long can you hold your breath? That depends basically on the individual tolerance to hypercapnia and hypoxia, also to the metabolic rate. Obviously, if you can lower your metabolic rate, the apnea duration will be longer, the breath hold will be longer. The capacity to store oxygen and carbon dioxide, and finally, the psychological tolerance to the unpleasant sensation of asphyxia. So this has been measured, and typically during apnea it's been distinguished clearly in two phases. The easygoing phase, that's easy, you start the breath hold here. The easygoing phase up until the physiological breaking point, and then you have the struggle phase. What this is actually representing is the movements, the respiratory movements associated with the respiratory muscles. And you see that basically this is the period, well, no problem, you hold your breath, and then it's the urge to breath that kicks in. And what determines the end of the apnea is what's called the conventional breaking point. And that's the point where you give up and basically start breathing again. The physiological breaking point is mostly dependent on physiological factors. And that, the most important one, is the alveolar PCO2, the partial pressure of CO2 in the alveoli, which is typically, for the measurements that have been done, it's typically around 46 millimeters of mercury. So when there is an increase in CO2 up to 46 millimeters of mercury, that's what's called the physiologic breaking point. Does that mean that you have to stop your apnea? No, obviously not. You can continue for a longer or shorter period of time. And of course, during this period of time, PCO2, the partial pressure of CO2, will continue increasing, right? Because basically, the lung will continue going into the lungs, and CO2 produced at the tissues will be unloaded there and accumulated because you're holding your breath. You're not getting rid of the CO2. The struggle phase is actually highly variable and is dependent on physiological and also on psychological factors. That's where the training, the experience in doing apneas kicks in. The feeling that I can hold it longer. It's known that basically the conventional breaking point, and these are the strategies that are used, of course, can be affected by different maneuvers such as swallowing, Valsalva maneuvers, squeezing a rubber ball, or mental arithmetics. All these can actually delay the conventional breaking point and extend the duration of the apnea. What is it that makes a breath hold to terminate? Essentially, PCO2. The measurements that have been done reflect that the PCO2 at the end of a breath hold are around 43 to 53 millimeters of mercury, and the partial pressures of oxygen are more variable between 46 and 80 millimeters of mercury. Notice that there is still plenty of oxygen here at the termination of the breath hold. Sorry. For a given individual, the partial pressure of CO2 in the alveoli and the end tidal CO2 is constant. And that is actually irrespective of the water temperature or the conditions of the dive. The longest breath holds that can be achieved are actually reached with oxygen inhalation. Oxygen inhalation before the dives, and of course, if you do that, if you are fully oxygenated, you breathe oxygen, you don't breathe air, you breathe oxygen. The danger then is that the CO2 levels in the alveoli will increase much more and reach as high as 102 millimeters of mercury. Thinking in terms of breath hold, I'm talking always about humans here. We'll move into animals later on, because basically all these breath holding experiments can be done rather easily in humans. And then we consider the topic of the oxygen stores. For this, we can calculate it rather easily. A 70-kilogram man with a total lung capacity of 5.5 liters and an alveolar PO2 of 120 millimeters of mercury will have an oxygen store about 2 liters. 2 liters of oxygen can be stored in the lungs and used presumably during breath holding. This is the total oxygen store. Only a bit less than half corresponds to the lungs, 820 milliliters. Similar amount in the blood, 880 milliliters. And myoglobin stored in the muscles, 240 milliliters. And then physical solution in the tissues, based mostly in the plasma, will be around 56 milliliters. So this is the total amount of oxygen, about 2 liters, the total amount of oxygen that you can have, or that a human in these conditions basically will have. If now you incorporate here the metabolic rate, say that the oxygen consumption, metabolism is around 300 milliliters per minute, a straightforward calculation tells you that you will consume these 2 liters of oxygen in about 6.5 minutes. So for the normal oxygen that's present in the body, that would actually give you 6.5 minutes. How can you extend it beyond that? Well, basically, the easiest way is to lower your metabolism, right? If you decrease your metabolism, you will be extending it by that time. Increasing lung stores. By pure oxygen breathing, you can extend this time, because now you put oxygen in your lungs. You don't put air. You add that, and basically, you can extend this substantially. The current record is 22 minutes. So apnea while breathing oxygen, you can extend it more than double it up, basically from the records we saw earlier. Now we have to start changing our... One thing is to hold your breath, the other is to dive. There are obvious differences here, but because during diving, when at depth, there is changes in alveolar partial pressure of oxygen as well, or when absolute pressure changes. If the absolute pressure at depth increases, the partial pressure increases correspondingly. And that's basically using Dalton's law that you should be aware of. What this has as a, well, put it on a calculation. 17% of oxygen on the surface would be equivalent to 121 millimeters of mercury. If you are at 50 meters of depth, that is actually much higher, 764 millimeters of mercury, of only the partial pressure of oxygen. Essentially, this makes that more oxygen from the lungs can be used while you are descending. And that increases breath holding time. The problem in this situation, the problem with using oxygen deep down, is basically what's called the hypoxia of ascent. Because the same way that as you go deeper, there's a higher partial pressure of oxygen because the pressure increases. When you return up, that partial pressure of oxygen keeps decreasing because of the pressure. So when diving deep, if your alveolar partial pressure of oxygen drops to 1.5% of oxygen, say, this is equivalent to 68 millimeters of mercury at 50 meters. But when you are ascending, this becomes only 30 millimeters of mercury. So this is a much lower. This would be at 70 meters. Just this low partial pressure of oxygen can lead to loss of consciousness and drowning. So the problem of diving deep with breath holding is that, yes, you gain when you go down because the pressures increase, but you lose when you go up, because then the very low pressures, because you have been consuming, keep getting lower when you are ascending. The same thing happens with CO2. The same thing happens with CO2. CO2, because of the pressure, also keeps decreasing when you are ascending. And that means that there is a decrease in the urge to breathe. During extreme dive, now if you put this at the extreme, it would be possible to show that theoretically there is a reversion in the oxygen diffusion. Because of the changes in the partial pressures, it would be feasible to show that theoretically oxygen, instead of moving from the lungs, from the alveoli into the blood, moves the other way around. You are losing, in an extreme dive, you could be losing oxygen from the bloodstream into the lung because of the low partial pressure of oxygen in the lungs. And this is when we are getting into the shallow water blackout and the concept of CO2, carbon dioxide stores. Because hyperventilation, if you hyperventilate before breath holding, there is an extension. Apnea can be, or the breath holding can be kept for longer. But that's not because you gain much more oxygen. Because when you hyperventilate, the only thing you can do is to saturate the blood more, right? How do you saturate the blood more? Well, in normal conditions, most of us, if you are healthy, your blood will be saturated 98% at least. So you can gain a marginal of 2%, which is very little. So hyperventilation is actually not due to increasing the oxygen store. But hyperventilation prior to breath holding works, extends apnea, because instead you are getting rid of CO2. And by getting rid of CO2, basically you fool your body thinking there is less CO2. You don't have to breathe that soon. As I said, despite the increased oxygen in the lungs, notice that I'm talking here about breathing air. If you hyperventilate with oxygen, yes, you win. But we are talking about hyperventilating in normal conditions. So hyperventilation extends apnea, not because you gain oxygen, but because you lose CO2. Forceful pre-dive hyperventilation. The fact that before diving, you forcefully hyperventilate. That will delay the hypercapnic respiratory drive long enough for hypoxia to cause loss of consciousness. So what happens here is a balance. You have hyperventilated, you have eliminated a lot of CO2. This CO2 now will start increasing during breath holding, but at the same time oxygen will decrease. Before your CO2 tells you it's time to be back to breathing, your oxygen has dropped low enough, and then there is a loss of consciousness associated with that. You can, and in these terms, when we look for human divers, the ultimate population we are always compared with are those of ama divers. Ama divers is basically some populations in Japan that have been for centuries fishing for pearls in oysters. And it's done by women, and they are repeated dives, so they will spend hours at sea, basically diving down, trying to find something, coming back up, down, up. So they are considered the best divers among human populations. In these populations, we know, it's been known, actually they do not hyperventilate before diving. They just do it repeatedly, and hyperventilation is not an issue. Here you have a little bit of the picture of this shallow water blackout we are talking about, associated with hyperventilating before diving. This is the situation on the surface, upon descent, holding your breath, and ascending again. What you see here is basically regular alveolar partial pressures of oxygen around 120 or 25 for CO2. In this case, there's been hyperventilation. Hyperventilation basically explains the increase, otherwise you would expect around 100. So hyperventilation, and you have ventilated out more CO2. Remember that the alveolar CO2 partial pressure is usually around 40. So instead of 40, hyperventilation has made this lower from 40 to 25. Then you descend, and notice that partial pressures increase. Why? Because of the pressure. Right? You are at depth. Because of the pressure, these pressures increase. And then you hold your breath. While holding your breath, what happens? Oxygen is transferred into the blood, and CO2 is downloaded in the alveoli, right? Notice what happens here. CO2 increases to 50, oxygen decreases much faster to 40. When you are going on ascent, because of the changes in pressure, this from 40 you go down to 32. CO2 also decreases slightly. But notice that what you don't see here is an accumulation of CO2, because you eliminated a lot in the beginning. So the main mechanism to explain shallow water blackout is actually related with what I was saying. Hyperventilation before breath holding eliminates CO2, and then what that means is that when holding your breath, oxygen partial pressure goes down too much before CO2 increases. There is no drive for ventilation. Your body feels there is no need to ventilate yet, but then you lose consciousness because oxygen is the one that is becoming limiting. And this is the mechanism as we understand it for shallow water blackout today. Thank you very much. And time for questions.